So I wanted to show you how to add vectors, subtract vectors, and multiply like a vector and a scalar. All right. So I would just start with like our basic equation for constant velocity motion. It's going to be position equals average velocity times time plus our position at 0 seconds. And this first position is position at our final time t. And if you recall, this is a vector, this is a vector, those are both positions. Velocity is a vector. Okay? Because position and velocity both have information about direction as well as amount or magnitude. So look at this term right there. You can see how you're multiplying time, which is actually a scalar quantity, and you're multiplying that with velocity. Sorry, and velocity is a vector quantity because velocity has information about which way you're moving and how fast you're going. That's an amount and a direction, or a magnitude and a direction. Time, however, is just an amount because time starts at 0 and always moves in positive direction to us. So the question is, what happens to a velocity vector when you multiply it by time, right? So let's say this is my velocity vector. I'm just making this up. And let's say it has a length of like 3 meters per second. That would be a velocity vector, right? Well, if time just so happens to be 1, and you multiply 3 meters per second by 1 second, you get a new vector. So let's say after 1 second, then what is velocity times time? So the velocity vector times t is what, right? Well, the direction of the vector doesn't change. The length of the vector doesn't change, but these units will change because the units for velocity are meters per second. The units for time are seconds. So the units change slightly. You're going to have the same length vector, but this will have a length, it'll still have a length of 3, but now it's 3 meters, okay? And that's our velocity times time vector. Notice when I multiply these vectors together, sorry, my bad, when I multiply a vector, which is velocity is a vector, times a scalar, like time, notice that I get another vector, right? I don't get just a number. I've still retained information about the direction I'm moving. Actually, it's not direction I'm moving anymore because it's measured in meters. It's really a displacement vector because it's measured in meters. And if you recall from the area of our velocity graph, I'm going to do this in a different color. If you recall, velocity graph's area is displacement, and displacement is calculated by v times t when you have constant velocity motion. So really this is a displacement vector of 3 meters. So when you multiply a velocity vector times time, you get a displacement vector. And that's after 1 second. Now let's see what would happen if it were half of a second, right? So if you had a velocity vector, same vector, say it's like 3 meters per second velocity. The question is, what does your velocity times time vector look like, right? And this is, what did I say, half of a second? So half of a second would mean that I have to cut this vector in half. I'm not going to change its direction, but I'm going to make it half the length, right? So now this vector has a length of 1.5. Now, since I'm multiplying meters per second times seconds, when I multiply a velocity vector times time, the numbers have units associated with them. And when I scale a vector, by a scalar like time, when time scales velocity, it does change the units, and 1.5 becomes 1.5 meters. Okay, and again, that's a displacement after half of a second. Now I can play the same game to multiply a scalar like time by a vector like velocity, and let's have the same 3 meter per second vector. Okay, and now I'm talking about, I don't know, 3 seconds or 5 seconds. Maybe I'll think of a bigger. No, that's going to be hard to draw. Let's just do 2 seconds because it's easier to draw. So if I want my velocity times time vector, my VT vector, it's going to have a length. This is after 2 seconds. It's going to have twice the length as my original velocity vector. And that's because I'm multiplying velocity, 3 meters per second, times time, 2 seconds. So I get a vector of length 6 meters. Okay? So this vector now has a length of 6 meters. And that's our displacement after 2 seconds. Okay? Now that's multiplying a scalar and a vector. It doesn't get you a scalar. The information about direction is retained, so you're left with a vector. Okay? And there are other ways of multiplying, like if you have 2 vectors. That's a little more complicated. We're not going to do that right now. Right now I'm just talking about multiplying a vector times a scalar. So that's multiplication. Now let's talk about adding vectors. Okay? Let's say I have a vector like, I'll just look at that equation. Okay? Go back to that equation. Position equals VT plus initial position, right? And the position in the beginning is at the end, right? And again, I'll just remind you that this is a vector, this is a vector, and this is a vector. So the first simple example, I'm just going to make it up. Let's say it's 1 second, and let's say the velocity vector is still 3 meters per second, right? But I also need a starting position. So I'm just going to make up numbers, okay? So let's say the velocity vector has a magnitude of 3 meters per second in the positive direction, okay? And let's say time is 1 second. And let's say I started at a position of 5. I'm just making this up, 5 meters, because of position. So it's positive 5 meters. So I'm on the right side of 0, right? Well, I incorporated direction with positive, negative here. So I could, and many of you will find it very easy to just use positive, negative for direction. And a lot of examples that'll work. So I go 3 times 1 is 3, and the units become meters, plus my 5 meters. And that gives me a final position of what, like 8 meters? And this is after 1 second, right? So if I start at 5 meters and I'm moving 3 meters per second, then after 1 second, I'll be at a position of 8 meters. Now that's the algebraic way of doing the problem. I want to show you how to add vectors. So I want to add this vector with that vector, okay? Well, my VT vector has a length of 3, right? So my VT vector should look like this, right? That's my VT vector, okay? And it has a length of 3. Actually, that's too big. It's going to cause a problem. I'm going to do this below. Okay, so say this is my VT vector, and it has a length of 3 meters, right? Because I'm talking about 1 second, and my velocity is 3 meters per second. I multiply those together, and that's the length of my VT vector. Now my initial position vector has a length of 5, right? So 5 would be about like this long. And what I'm going to do is I'm going to place the vectors head to tail. This is how you add vectors. You just draw them head to tail. So this is my 5 meter, my vector with a 5 meter length. That's my initial velocity, initial position, sorry. So 5 meters is my position vector at my position at 0 seconds, and 3 meters is my VT vector. And that means I'm really, what this equation is doing, if you really think about it, VT is my displacement. X naught, or X with a little 0, is my initial position. So really you're just taking your initial position and you're adding your displacement. Well, if you take your initial position, add your displacement, don't you just get the position where you're at? Like later? So basically the 3 meters is my displacement. This vector here is my displacement. The 5 meters is where I was in the beginning, right? Okay. My position at 0 seconds. Now, the rules for adding vectors are very simple. Place vectors that you're adding head to tail configuration. I already did that. Now, to get the vector that you get when you add these vectors, you need to draw a new vector. You need to start at the tail of the first vector. That's the 3 meter vector. So start at the tail of the first vector, end at the head of the last vector. That's the 5 meter vector. So I'm just going to draw a brand new vector that starts at the tail of the first vector and ends at the head of the last vector. And this new vector, you can just see looking at it that you have to add 3 meters plus 5 meters, right? And when I do that, I should get 8 meters. And that's the length of my final position vector. And it makes sense that my final position vector would be 8 meters in length. Notice it's the same thing we got before. Only difference is below, like down here, I'm using a completely different approach. I'm basically adding vectors. And vectors are kind of cool because you can add them in either order. If I wanted to, I could have placed the 5 meter vector, then the 3 meter vector, like this. All right? So that was my 5 meter vector. And this is my 3 meter vector. And I would have gotten the same thing. Nothing special would have happened. It's exactly the same. And I would still get an 8 meter vector. Okay? So again, the basic logic of this equation should totally make sense. You're simply adding where you're at plus however where you're at changed. The way that where you're at changed is your displacement. So you're adding where you were plus your change in where you were. That gets you where you're at now. Or final position is just where you were plus your displacement or your change in position. Anyway, so that's how you add vectors. I got one more for you. Let's say you wanted to subtract vectors. Now, the way this might go down is, let's say you have an object where 0 is here, okay? 0 is like right there. And let's say you're starting over here at -5, and these are positions x measured in meters, okay? And so let's say your object starts at some negative position. So I'll just draw my object right here. And let's say you're going in the positive direction. And I'm just going to try to be simple, make up the same kind of numbers. Let's just say the velocity is 3. Sorry, that's the speed, 3 meters per second speed. Okay? So I'm just going to, for fun, figure out where my object is at 1 second, right? So I'm going to start with my general equation that came, this vector equation that describes my final position, or my position at any time t. Now I'm going to use 1 second just because it's so simple. So it's average velocity, which is a vector, times t plus my initial position, right? Well, you can see right away what's going to happen here. When you put numbers in and do this algebraically, which is how you would probably do this problem, you would have positive 3 meters per second for your velocity. Notice I'm incorporating direction with the positive. And then times 1 second, right? That's my time. And then I'm adding my initial position, but my initial position in this case is negative 5 meters, right? So you can see what happens when you do this algebraically, right? My final position is actually going to be equal to 3 meters minus 5 meters, right? And when I calculate this further, I get like negative 2 meters, right? And that's my final position. Okay? So I've solved this algebraically. Now let me show you how it works out by adding the vectors, okay? So I got a v times t vector. That's this term, right? My average velocity is to the right, yeah? And this is after 1 second, let's say, to make life easy. So I'm solving for the same exact thing. I'm still going to get negative 2 meters for my final position. I'm just going to show you using vectors, okay? So v is 3, t is 1, so I get 3 meters as my displacement vector to the right, yeah? So my displacement vector to the right should be 3 meters, yeah? Actually, that's too long. I don't want to make it that long. I'll make it a little shorter. So I got a 3 meter vector to the right. That's 3 meters by scaling my velocity vector with time. Okay? Now, I need to take my initial position vector, right? Well, if I look on my axes, sorry, on my number line, my bad, you'll see that your initial position vector looks like this, right? That's my initial position for the car. And you can see it's a length of 5 meters to the left. So I'm still going to place my vectors head to tail, okay? So I'm going to start my initial position vector at the head of my 3 meter vector. And I'm going to draw to the left, but now it's 5 meters long. So I've essentially done the same thing. I've placed the vectors head to tail, okay? I drew my initial position vector, right? So I just do the same thing. When I add these, I need to start at the tail of my first vector and end at the head of my last vector. I get a vector that looks like that. That should be my final position vector. And if you look at that, it's got to be 2 meters in length, right? So you can see just looking at this that I would subtract my 5 meter long vector minus my 3 meter long vector. So I'd be getting 2 meters for the length of my final position vector. Okay, so and notice that vector, that final position vector, points to the left, so that's why final position is going to be equal to negative 2 meters. It's a vector that points to the left, and it's 2 meters long. And notice that's the same thing we got right here. Okay? So that's a basic idea of how you add vectors. You just place them head to tail. And then you draw a new vector from the tail of the first vector to the head of the last vector. Okay? And that vector you draw from the tail of the first vector to the head of the last vector, that new vector is like what you get when you add the vectors. And of course it's a vector. This approach of adding vectors by placing them head to tail and then drawing a new vector from the tail of the first vector to the head of the last vector, this is called the head to tail method. So feel free to look up head to tail method of adding vectors. It's geometric vector addition is another name for it. Feel free to look up this topic on YouTube, and you should find a million videos about it if you're not feeling particularly strong on this topic. But you'll just need to practice and get used to it. The other thing that might happen someday is let's say you got vector A and vector B. Okay? Let's say I want to add them. Well, I'm just going to draw vector A and place it head to toe with vector B. I'm just redrawing my vectors head to tail. So what I would get is this vector, which is vector A plus vector B. Okay? So it's A plus B in length, right? Now what if I wanted vector A minus vector B? How would I do that? Well, simple. Instead of drawing vector B to the right, I want to take vector A minus vector B, so I'm going to reverse the direction of vector B, but try to draw it the same length. So that's as minus vector B. That was vector A. And now when I add these, I start at the tail of the first vector, which is vector A, and I end at the head of the last vector, which is vector B. Now what I like to do when I'm adding vectors, I didn't say this before, but I like to make my vector that I get when I add them look different. So I have a strategy to help myself understand where when I draw what I get from adding vectors, notice I made this arrow look differently. I think that'll help you. So the vectors I'm adding, I draw as arrows. See, these are just drawn as arrows, plain old arrows. But the vector I get from adding vector A and vector B, I draw as a bold, fat thing. I make it look a lot different to emphasize the fact that that little vector I drew, that's what I get when I add vectors. Because sometimes it can get confusing, especially when you're adding more than like 2 vectors and you're adding them all up to get something. It's nice to highlight it and emphasize it and make sure that the vector you get from adding the vectors looks different than the vectors that you are adding. Anyway, those are some strategies and tips. Hopefully that helps. And yeah, thanks for watching.